What's up, fellas? So today I want to be introducing this trapping rainwater question. Let's have a look. You're given an array of non-negative integers height, this thing, which represent an elevation map, okay? Each value, height I, represents the height of a bar, which has a width of 1. Gotcha. Return the maximum area of water that can be trapped between the bars. So if you look at this array, you have 0, so the height of this is 0, and the second element is 2, so the height of this is 2, and then the next one is 0, and then the next height is 3 here, as you can see, and so on and so forth, right? So that's what they mean by the elevation map. Now, what do they mean by maximum area of water that can be trapped between the bars? So if you were to imagine like rain pouring down heavily, right? So you'd have water coming down here, and then it kind of like spilling over there, and then it dissipate, right? But some water might fall in here, might fall into this crevice, and because it's being blocked by these two walls, it's able to hold water. Similarly, if you had water that falls here, and then, well, obviously there's no walls or anything like that to hold it, so it has to like spill out, right? And then that same water could flow down here. And because the water in this basin is being trapped by these walls, it's able to contain that water. It's able to be trapped, right? And likewise, water that comes here would kind of flow down and disappear, right? So it cannot be held. So it cannot be held because we don't have a wall here. This just kind of falls off into the void. So given this kind of height map, we want to calculate how much water can actually be trapped. We want to know how much water can be trapped between these bars, right? So let's have a think about how we can figure that out. Maybe not programmatically yet, but just like using our intuition, right? So if you look at this pond of water, what do you see? Well, you see a water of height of 2. Why is the height 2? Well, that's because we have a wall here, that's height 2, and a wall here, that's height 3. And then this is looking a little bit familiar with the container with most water question, because we would take the minimum of the left wall and right wall, right? And then that would give us the height of the container here. Okay, so that's pretty easy. Let's have a look at this one next. This one looks a little bit different. This one looks a little bit more difficult to define, but it's possible. So we know that this has a height of 2, but why does it have a height of 2? Well, that's thanks to this wall, obviously, which has a height of 3, and the other wall that's blocking it is this one, right? Which has a height of 3. And at this index, we also have this little block on the bottom at the height of 1. So obviously, if the water comes down, it will be blocked by these walls, so the water stays trapped. But because of this one block on the bottom, water obviously can't occupy the space. So the total of it will become, I guess, the minimum between 3 and 3 minus 1, right? So that's why we have the height of 2. Okay, that makes sense. So let's look at another case. So what about this middle one? Well, I guess it's a similar story to what we just looked at before. It's thanks to this wall here, trapping the water, and this wall on the right with a height of 3. But at this index, we don't have that 1 here, right? We don't have that block here, so water is able to go all the way to the ground. So that's why we take the minimum of 3 and 3, and that's the amount of water at this index. Well, let's look at something that doesn't have water, for example. Let's have a look at this index then. Why doesn't this index have any water? Well, if you think about it, we have a wall here, but there's no wall on the right, which means that this cannot be a container to trap water. And as for this thing, similar scenario, we got a block here, height of 3, but we have nothing on the left to protect it, so no go. So we're getting kind of the intuition here, but how do we represent our analysis in a nice little formula? Well, if you really think about it, we do take the minimum of the left and the right, but if you notice, we don't necessarily care whether the wall is directly to our left, whether it's 2 units to our left, whether it's 3 units to our right. It doesn't really matter where the wall is placed. And also, technically at this position, this is kind of a wall, isn't it? But we don't count that. Why is that? Well, that's because we want the maximum height of a wall to our right and the maximum height of the wall to our left, and then we take the minimum of these two. So I'm gonna write it out. We want the minimum of the maximum height on the right, I'll call it max right, and the max left. And that'll give us the 2 walls that will create a basin, and we have to minus it by height I, right? Which is this thing. Now that we have the formula to figure out the amount of water at any given index, how are we going to use this to calculate the solution? Okay, what if we run a little brute force algorithm? What if for every single element here, we loop through the list of heights, and then for each one, we compute the max right, and we compute the max left, take the minimum of that, and then just minus the height at that index. Okay, that's definitely possible. So I'm going to pick an arbitrary point here. Let's say we're at I is equal to 2 at this position. So we're basically asking to take the maximum between these and the maximum between these, right? And likewise, once we have that, we want to take the result of this and then we feed it to the minimum, okay? And then repeat that for every single other element. So let's think about the time complexity of something like this. So at any arbitrary index, I have to take the maximum of everything that came before me and the maximum of everything that came after me, right? So for I, blah, 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 and this was just gonna loop through heights. Then I need to write a for loop in range from 0 to I, right? Which will be this left part. This is how we get the max left. And then we have to write another for loop that goes from I plus 1 to the end, basically. So then I to get the max right. And then the min operation and this operation is O of 1. So we don't really consider those. So effectively for every element, we're gonna process the entire list, right? So what's the time complexity of that? Obviously, it's O of n squared to run this brute force algorithm, right? And the space complexity is O of 1. But let's move on to a better solution. Now, there is a problem that I've done on this channel before, and that problem is called product of array except self. If you've done that question, you'll notice that the setup is quite familiar. For each index, I want to do something with every other index except itself. So the optimal solution to that problem was to do the prefix suffix method, which goes kind of like this. We're going to create an array called prefix, which is just going to be empty initially. And then this array is going to be as long as the heights array. And then for each index, I want to calculate the maximum of every number to the left of it. So we're calculating max left for every I, right? And then once we have that, we're going to combine it with a suffix array, which is going to calculate the max right at every single index. So let's do that. I'm going to create a variable called max left. Well, obviously, initially it's 0. We haven't processed anything after all. So then we're going to write a for loop for h in heights. So let's have a look. Let's just use our eyes a little bit here. So at the first index, I equals 0. What is the maximum of everything to the left of it? Well, obviously, at this point in time, nothing, because there's nothing to the left of I equals 0, right? That just happens to be the same as what we have right now in our variable. So I'm going to go append that to prefix dot append. So that will turn prefix into something like this. Okay. Oh, sorry. I meant append max left. Then I have to update max left is equal to the maximum between h and max left. So is it going to take the max between 0 and 0? Well, obviously, then it doesn't change. That's no problem. Then we move on to the next iteration, the next h, which is 2. Now for 2, we ask the same question. What is the maximum left of everything to the left of it? Well, we can see it's 0. So that also gets appended here. And then max left will be updated between the max of 2 and 0. Right? This will get updated. And same thing again, what is the maximum of every element to the left of it? Well, obviously, just using my eyes, it'll be 2. And so on and so forth, right? Let's fill this out. There you go. We've completed our prefix array. And now let's move on to our suffix array. And this time we're going to work back to front. And initially max right is 0 because since we're starting from the right side, if we ask the question, what is the biggest element to the right of this is, well, nothing. So it's 0. And then once we move our pointer here, this would have been updated to 1, right? So what is the largest element to the right of this index? It's 1. And so on and so forth. It's basically the same thing as prefix. And there you go. Once you have the prefix here and the suffix here, we have the max right for every index and the max left for every index. Then we just loop through them simultaneously and we combine them with min. And that'll give us this thing. So we just take the minimum of this and this, this and this, this and this, and so on and so forth, right? And we can minus that with the heights I. So what is the minimum between this and this? Well, that's 0 minus the heights at I, which is 0 here. And that will give us the water at position 0, which is 0 here, as you can see. And then we move on to the next index. What is the minimum between 3 and 0? Well, that's 0, and then minus the height here, which is 2. That will give us, well, -2 actually, but I'll just put 0 because there's no such thing as negative water, right? So the next index. So for the prefix, we have 2 here. For the suffix, we have 3. And then we take the minimum of 2 and 3, and that'll give us 2. And then that will minus heights I, which is this thing, right? 0. 2 minus 0. Hey, that's 2. And then that tracks, see? We have the height of 2 here. And then next iteration, so the prefix here is 2, and then this is 3, which will give us 2 minus this thing, which is 3, -1, right? So this thing's too tall. So it's 0 water here. And then I'll do one more example just to really hammer it home. We have the max left at this I, which is 3, and we have the max right here in the suffix, which is 3 as well. And then the minimum of these two will give us 3, right? Minus the height at this location, which is 1, which will give us 2, which again, it tracks, right? So you can see how this works. It's an optimization method that's similar to the product of array except self problem. If you're a bit confused by this, then you can have a look at that problem too, because this problem uses the trick from that question. So what's the time and space complexity of this? So luckily our time complexity has improved. It is now O of, let's see. So we make an array that's the size of heights, right? And then we're gonna insert it. We're gonna insert into this thing. And if you look at the operations in this for loop, appending is an O of 1 operation, and taking the max between two elements exactly is a O of 2 operation, but it's in constant time. And then you multiply that by how many elements we're processing. We're processing n elements, right? Because height is our input array. So this thing is O of n, and since suffix is a similar calculation, it's also O of n. And then also running this for every element is also O of n. So in all, our time complexity is 3n, which we will simplify down to O of n. And as for our space complexity, that'll be O of n as well, because we'll need these arrays that scales to the size of our input array. That's pretty good. We got a better time complexity in exchange for a little bit of memory. So the optimal solution is actually O of 1. So there's a solution that's even better than this. But how do we get there? Let's take a look. So I want to introduce to you a third way of doing this. I've got the code on the right for me. This is going to help us explain a little bit. And then actually, this method is actually going to be using the 2 pointers. So if we have an L and an R here, we're going to initialize that to start. And then we're going to keep track of 2 variables here, max left, which is going to be set to the height at L, which is 0 here. And then we're going to keep track of max right. This will make sense in a moment, which is length of height minus 1. So the final index, right? Now the first line here, this is just, 2 pointer things, while L is less than R. And then the next line, we have this if check. So let's see what this does. So it's asking whether max left is smaller or equal to max right. And in this case, well, it's smaller, right? So by knowing that max left is smaller than max right, that gives us permission to process this element. Now conversely, if max right were to be smaller, then we will be processing this element instead. But what do I mean by processing an element? Let's keep going. So we'll move this L 1 unit to the right, and then we're saying water, which is the total amount of water trapped inside the structure, we're gonna add this thing. This formula, a max left minus height L, computes the amount of water at this index. Now you might be asking yourself, but wait, didn't we have a formula from the brute force and the prefix suffix arrays solution that kind of looks similar to this? So let's have a look at that formula. So if you remember, that formula goes something like this. Water plus equal the minimum of max left and max right, and we subtract that by the height at I, right? This was the formula that we had, and it looks awfully similar to this one. The biggest difference is that we're no longer using this min. We just straight up know somehow that the minimum between max left and max right is max left. We just know. We don't even have to compute this, so we just take max left and minus the height at L. And similarly, if you look at this chunk of code in the else branch, it reads really similarly, doesn't it? We don't even bother calculating the minimum anymore. We just know that max right is the smaller of the two, and then we're just gonna yoink that and use that in our calculation here for the water. Also, as a small side note, this max 0 here just means that sometimes when we subtract these values, we might end up with a negative number. And so we don't actually want to subtract the amount of water that we have. So we just round up any negative numbers to 0. But back to the most important thing, how are we able to just discard the minimum calculation altogether? Let's take a look at some facts. So since we're executing in this branch, one thing we know for sure is that max left is smaller than max right. So at this point in time, at this L, well, more accurately, before we even execute this, L was here, wasn't it? So we know that at L plus 1, once we increment it, it'll be L plus 1. At this index, the maximum height of everything to the left of L is 0, right? But the max of everything to the right of L, we don't really know. But if we just have a look at it with our eyes, we know that this is 3. The maximum height of everything to the right of L is 3. But we have this recorded at 1. So what's up with that? Well, at this point in time, the max left does represent, the max left that we know of in the brute force and in the prefix suffix array solution. But the max right is not accurate. This is accurate. This is not accurate. This should be 3, but it's 1. But the thing is, we don't need this to be accurate to know that when we run the min operation, max left is just straight up going to be smaller than max right and will dominate this, and we don't even need an accurate max right value anymore. And that is because, let's say we were to calculate the quote-unquote true and accurate. So let's just say we start decrementing r by 1 to the left each time, and initially, max right will be 1, and as we discover this bar, it gets updated to 2, discovers this bar, updates to 3, and then once we get here, because the height at this index is just 1, and well, if you take the max of 1 and 3, you get 3, right? So the smaller number stops mattering. So it's basically irrelevant. The max is going to be 3 all the way here, right? So once we reach this point, we can conclude that it's all 3. Due to the nature of how max works, this number can only go up or stay the same. It can never go lower. So because max right can never get smaller, and we've already established that max left is smaller than max right, it means we can safely conclude that the minimum between max left and max right for this L will always be max left, right? Max right can never win because max right can only grow. That is the crux of this optimization. So back to the beginning with L here, and we have these values initialized. So we compare max left and max right, okay? And it turns out that max left is smaller. So we're going to process L plus 1. So we're going to increment L and process this thing to calculate the amount of water in this thing, right? So we're going to take the max left, which is 0, and then we're going to subtract that with the height at this point in time, which is 2, which will give us minus 2. And thanks to this max function, we're just going to round it up to 0, right? There's 0 water at this index. Okay, great. And then the next step here is to update our max left, which is going to be the maximum between 2 and the current max left, which is 0. So 2, right? Max left will be updated to 2. All right, next iteration. Let's go. We're going to do the same check. Is max left smaller or equal to max right? So max left is 2 right now, which is all this. The max of all this is 2 right now. And the max right, which is the max of all this right now, is 1. Obviously, 2 is not smaller than 1. So we get to see what happens in this else clause. So we're going to move the r one value to the left to r minus 1, right? That's going to be our new r. And at this index, we know for a fact that the max right here is 1. This is accurate. And the max left is, well, that we know of so far, is 2. And since this 2 can only grow or stay the same, but never decrease, we can be sure that we don't need this max left anymore for this min calculation. Then we can just use the max right value as is. So let's go do that. Max right now is 1 minus the height r, which is 2, equals to minus 1, and which gets rounded up to 0, right? So once again, no water in this position. All right, now I want to see an example that does include water. Hopefully we can get that. Oh, and before that, we do have to update our max right, which will take the max between the height of this bar and what we have so far. This is going to be updated to 2. Okay, so next iteration. Is max left less than or equal to max right? Well, the answer is yes. So this executes. Now, since these values are equal, can we employ the same strategy as what we've been doing so far? So let's have a little think about this. Let's have a look at it from the perspective of the element that we're going to be processing. So let's say this is going to be the next element we're processing if we decide to go down this branch. So we know at this point, the max left here would be 2, and then the max right that we know of so far is at least 2, but can be more. So what's the minimum calculation here? So the minimum between a 2 for sure and a 2 possibly more will be 2. So we can safely take max left here, and we can still discard max right as usual. So that's safe. And let's say we think about it from the other side. What if we decide to handle the equals case in this branch? Let's say we end up moving r to one element to the left, so it'll be here. Then from the perspective of this thing is we know for a fact that the max right is 2, but for the max left, it can be 2 or more than 2, right? And the minimum of that will be max right no matter what. So what I'm trying to say is, in the case where both max left and max right are equal, it doesn't really matter which branch we handle this on. So I just kind of arbitrarily pick a left branch. So let's keep going. So max left is 2 and max right is 2. So we're going to be processing this index. Let's move it here. So we're going to take the max left, which is 2, minus that with the height of this index, which is 0, and that'll give us 2, which checks out, right? We have 2 blocks of water here, and our calculation returned 2 earlier. So great, we have 2 water now. That's really cool. And then honestly, we just kind of repeat this process for the rest of the indexes. Okay, so for this last iteration, because currently L is still less than R, we still run this last while loop. We're still gonna do this check, and we're still gonna execute this line, right? So we're gonna move L here, and then we'll calculate the water at this point. And notice that at this point, the code is actually going to calculate the water at this index, right? As it should. However, we've actually already calculated the water at this point. So we're actually gonna calculate the water at this index twice. I'm gonna be so real with you, bro. I don't know why this doesn't matter. Somehow at this last bar, the water in this bar is always 0, so it never affects the final answer. I actually ran this code in both leetcode and Neetcode. Like, it passed like every single test. So this code works. I don't know how I can convincingly say that at this last index, the amount of water in this last index is always 0. I don't know why. But it does work. It does work. I don't know. Anyways, this is gonna get processed twice, and it's not gonna matter for whatever reason. And then this while loop's gonna stop because L is now equal to R, and then it's just done. Yeah, we get our water. So setting aside that weird edge case, another thing that I want you to pay attention to is that we never calculated the water at this index or at this index, because this entire while loop did the calculation for all the values in between, but never the first nor the last one. Now, the reason being is because at the first and the last one, because there's no wall here, all the water is just going to spill out anyway, so we don't even bother calculating it. We only calculate the stuff like in the middle here, so they don't even enter our calculation, i.e. they have 0 water. And then one last thing about the code that we didn't touch is just this small check, because the input array might be empty, and if it's empty, we want to return 0. And as for the time and space complexity of this thing, well, we know that all of this is 01, and this while loop is running 2 pointers on every element in the input, and all the operations inside this while loop are O1 operations, right? So all in all, this thing is O of n. So the time complexity is O of n. And as for the space complexity, we're just using a bunch of variables. We're not using anything that scales with the input array. So all in all, space complexity is constant time. Since we already have the code here, I'm just going to execute this on like the grading platforms. So first one is this one on the usual Neetcode website. It works, very cool. And then I'm going to run this on leetcode as well. And this also passes. I'm still confused about the edge case, man. Anyways, that's all. Okay, bye.